Okay, so we will start today with another example on just to refresh our memories about how to solve transistor circuits. Okay, so just let's call it refreshing circuit. Okay, so let's choose another color. So it's a simple one. Here is we have 10 volts. Okay, this is RC equal to 47 kilo ohms. This is RB, and this is 330 kilo ohms. Okay, and beta is equal to 75. Okay, so let's again assume it is an active region. And again, when the transistor is in active region, then IC is equal to beta IP, VBE is equal to 0.7. Okay, and IE approximately equal to IC, or you can say it's equal to alpha IC, and alpha is just beta over beta plus 1. Okay, which is around most of the time 99% or 99. Okay, good. So let's apply this to this circuit here. Okay, so let's call this current I. And I solved this circuit, or I want to solve this just because of this observation. So usually RC, we show that IC usually flows in RC, which is the resistor connected to the collector. In that case, no. So the real definition of IC is the current that goes into the collector. And here is the collector. Okay, here is the collector of the transistor. So this is actually IC here, the collector. Okay, so this current here is different from IC. Let's call it I. This is I, this is IC, and here is IB. IB is the one that is flowing into the base. And IC is the current that's flowing into the collector. And apparently this guy here is not IC. So let's call it just I. Okay? But from this note, I equal to IC plus IB. One may say, oh, this is the emitter current. Yes, this is the emitter current. Just if we continue the circuit, if we draw the circuit completely like this, here is the 10 volt. So this current is coming that way. So it's actually the emitter current. Okay, if we draw the battery and connect it to the ground, and the ground is the emitter, we connect the emitter to ground here. So it's actually the emitter current. Okay, and we know that this is beta IB, and IB is still the same. So take IB as a common factor. So this will be beta Z1 IB plus 1 IB. Okay, so let's make Kirchhoff at this outer loop here. So if you just cannot imagine it, so I will draw it again for you. And we can, draw the battery like this. 10 volt, here is R C, here is RB, and here is the 0.7. So from this loop, which we call always the outer loop, from KVL, so let's call it loop 1, for example. So from loop 1, okay, 10 equal to I RC plus IP RP. So IB is flowing in that. So here is the direction of this voltage, here is the direction of this voltage, plus 0.7. And what is I? I is actually beta plus 1 IB RC IB again plus 0.7. This equation has only one unknown, which is IB. So IB can be in one on the left-hand side. If you do the simplification, so this will be 10 minus 0.7 over RB plus beta Z1 RC. Okay, if you calculate this, this will be very small, 238 microamperes. Okay. Then we need to check that we are really working in the active region. So we must check the VBC voltage. So first VC is equal to, remember this, this node is 10 volt. So VC is equal to 10 minus I RC, not IC RC. Okay. So 10 and I can be calculated easily. So I is just, IC plus IB, and IC is beta IB, so it's a beta plus 1 IB. As we said, I is just is just I emitter, or the current in the emitter, multiplied by RC. If we calculate this will be 1.486 volt. And VB is very simple. So B is the voltage of that node. I'm very sorry, guys. I don't know why it's acting weird like this. So let's see. Oh, very simple one. So this is the base. Okay, and we know that between the base and the emitter there is 0.7. So let's do it. So VBE is 0.7 in active region and also saturation. This is equal to VB minus VE. VE is 0, so the emitter is connected to ground. So this is equal to VB. So VB is equal to 0.7. So VBC equal to VB minus VC, 0.7 minus 1.486. This will be around minus 78 volts. So that means that J2, the collector base junction, is reverse bias, which is, matches with our assumption, in which we assume that we are working in the active region. So I solved this question for two reasons. The first one, to avoid a mistake that you might do. When I was a student, I did this, that I assumed that the current flowing in RC is IC, which is wrong, just I. Okay, maybe in the active region, maybe that will not make much difference in the calculations. I mean, the numbers that you will get with this incorrect assumption will be, very close to because beta is very big, and we are in active region. I see approximately equal to IE. Okay, but in saturation, no. In saturation, you will have a very big difference in big error in the calculations. Okay. The second thing here is that we always want to reduce the amount of power or the amount of batteries that we use to bias the transistor. Okay? And as you see here, there is only one source in the circuit. One source, just one battery. if we compare it to a circuit, for example, from the previous lecture, so there are, let's see. Yeah, this circuit, for example, has two sources. There is this source here, and there is also another source here. Okay, so why there are many circuits with different, shapes and connections? Because there is a purpose for each one. Okay, we want, for example, to reduce the amount of batteries that we are using to make our circuit much cheaper. Okay, and maybe we want our operating point or the Q point to be stable, as we will see, maybe after 10 minutes or something. Okay, so we connect our circuit in another way, and so on. Okay, okay, so this is just a refresh for the so for to what we have taken so far, especially last lecture and the lecture before, which is transistor analysis, NBN transistor analysis. So we connect in the transistors that we studied. It's called NBN so far. In which you have N here, N type silicon, then B type silicon, then N type silicon. And this is the emitter, so it has been heavily doped than the other ones. Can we do a BNB transistor? Yes, we can. So there is another transistor called BNB transistor, okay, in which we do the opposite of NBN. So we have now in this BNB transistor, the emitter is a B type and it's heavily doped as well. Then the base is N type, not B type like NBN. And the collector is again B type, but it's lightly doped than the emitter, or lighter doped than the emitter. Okay, so again, this is our collector, this is our emitter, and here is our base. Okay, and again, if we connect this is as a forward bias, and in that case, this is reverse actually. So we should, reverse the batteries. So forward means that the emitter or the B region should have higher voltage than the N region. So we should switch here the battery. And this is VEB now, not VBE. And again, to make the junction between N and B, base and collector reverse, we connect another battery here, which we can call VEC, and it should be larger than VEB, so that we junction 2 J2 here is in reverse. So in active region, again, just like NBN, G1 is forward, G2 is reverse or off. So let's call it more general, off, because it might be reverse and off. That's so off means either reverse or forward, but with now VCB, not VBC like the other one, is like NBN, is less than 0.4 volt. Again, because here is the relation between I diode or any junction and the voltage across the junction. And in that region here, we are forward and the voltage is larger than 0, but the current is very, very, very small because it's exponential relation. So we'll assume this is 0.4. The point at which the current will start to have, noticeable values. Okay, So, and again, when it conducts, the currents will be something like this. So we have, you know, a huge amount of holes, not electrons, emitted from the emitter. So the emitter now is emitting holes. Holes. In NBN, the emitter was emitting electrons. And a small number of electrons, you know, coming from the base to the emitter. And of course, the collector will collect these holes that came from the emitter. And again, although G2 is reverse, okay, but we could inject current through it. Okay. So IB is the current that, you know, compensate for these electrons. Remember that the direction of the current is the opposite to the direction of the electrons. So that IB is something like this, flowing in that way, opposite to the electrons, which constitute or make this current, IB. And IC is flowing out of the collector, not in the collector. And again, the IB is going out of the base, not in the base like NBN. And again, IE is flowing into the emitter, not out of the emitter like the NBN. So everything is opposite, okay? But the relations are, you can say the same or similar. So here, for example, in any region, IE always equal to IC plus IB. Okay, so let's start by active. So in the active region, IE is equal to IC plus IB. VEB is 0.7. Okay, and VCB should be less than 0.4 volt. And also for the currents, IE approximately equal to IC, or you can say beta over beta plus 1 IC, which we call this alpha IC, and the alpha usually 0.99 or something. Okay. Again, approximately. Good. Now, the second region is the saturation region. In which J1 and J2 both forward biased. VEB again equal to 0.7. VEC now, not VCE. Everything is, you know, is flipped. Instead of VBE, we have VEB. Instead of VCE, we have VEC equal to 0.2. And what else? But again, the same still. IE is still equal to IC plus IB. But now, in the saturation region, IC divided by IB is less than or equal to beta. And remember, based on this, this means that IE is not anymore, or I mean, this relation here doesn't hold anymore, which is approximately equal to IC. No. Okay, so don't use this one in the saturation region, only in active region. Okay. What else? Yeah, the last region is the cutoff, in which IB equal to IC equal to IE equal to 0. And why is this? Because there is no enough forward biasing on the base emitter voltage. So usually when we are in the cutoff region, that means that the base emitter junction is not forward biased, or forward, but, you know, very, very weak forward. So that means that J1 is either reverse bias or weak forward off. In other words, weak forward mean VEB, not VBE, less than 0.7. Okay? Okay. So let's go to examples. Okay, so example 1. So let's draw the circuit for this guy. So here we have. So usually, since IE is going into the emitter, this is also opposite in the directions of the battery. So in NPN transistor, usually you connect VCC, or the high voltage, the battery, to the collector. But here we usually connect the battery to the emitter. And by the way, I forgot to mention the symbol of, let's do it. So the symbol for this guy is like this. Okay, so let's continue. So I just draw the circuit. Okay, didn't do anything else. So let's now solve it. Okay, so we have here the base, we have here the emitter, we have here the collector. Okay, so let's again assume it's active region. Okay, before anything, because this is PNP and you have many confusion with it, like me. So first, before going into the solution, draw the positive directions of the current. IE should be going into the emitter. IB should going out of the base, and IC is also out of the collector. Okay, so this is IC, this is IB, this is IE. Okay, in the active region, VEB is 0.7, so the direction is like this. So VEB is 0.7. Okay, now ask yourself a question. Is there a source that can give the emitter a higher voltage than the base? Yes. Just draw the battery. It is the battery 10. Okay, so yeah, there is, in this loop, there is a source that can give this 0.7 to the emitter base junction. So it's probably in either active or saturation. It's very difficult. When you have a biasing, when you have something to provide this 0.7, it's very difficult to determine if it's active or saturation. So let's assume active first. Okay, good. So from this loop, let's call it loop 1, for example. Okay, you have 10 equal to 0.7 plus this voltage, which is IE RE. This is equation. This equation has only one unknown, which is IE. So from this equation, IE is equal to 10 minus 0.7 over RE. So IE is equal to 4.65 milliamperes. Okay. Now let's get IC. IC approximately equal to IE, or 1 over 100 plus 1, which is almost 1, IE. Okay, so it's equal to 4.6 milliamperes, again approximately. Now we need to check that our assumption is correct. So we must calculate VC. VC is the voltage of this point. So IC is flowing in that way. So this is the voltage across the resistor. So VC is equal to -10. This voltage here, it's not ground. Minus ICRC, or plus, I'm sorry. So this is going out to that way. So yeah, minus, I'm sorry. Plus, I'm sorry, plus. Plus, yes, plus. Okay. So both of these, so let's draw it again. So this is the collector. So this is the direction of the voltage of the battery, and here is the direction of, because the current is flowing in that way. So both are the same direction. Okay. The value of the battery is -10, and the value of this voltage is ICRC. So this is equal to -535 volts. Okay. We need also VB. VB is easy peasy. It's 0. So here is 0 because it's connected to the ground. So we need now to calculate VCB. This should be less than 0.4. VCB -535 minus 0 equal to -5.35. So that means that J2 is indeed reverse biased. Okay, so our assumption is correct. So this was a straightforward example, we can say. Yeah, one thing before leaving here, you notice something, that we didn't use this beta. We didn't use it. We almost didn't use it. In active region, not used. Okay. And that's actually say something about this circuit. That this circuit is immune, we can say, to the changes in beta. So there is a problem happens usually in transistors that beta, so some observation here. That beta is a strong function in temperature. I mean, when you design a circuit and you assume that beta is 100, okay, then you turn on the circuit starts to conduct, and there is currents and stuff. So usually electronic components heats up. So when electronic component heats up, the temperature changes. So beta will change as well. This is just physics. So in physics, there is some proof or something that says that beta is changing with temperature. So if your operating point is a strong function in beta, then when beta changes, also the operating point will change. So you might be designing your circuit to work in active, but because of the change of the temperature, it might go into saturation. And that's very dangerous because for some applications, we must be in active region. We must, like for example, amplification. And if your operating point going into saturation, there will be no amplification. Okay, you will see nothing on the output, as we will see in next week when we take amplification into details. Okay, so here this circuit is immune to beta. So this circuit, the previous circuit, is immune to beta changes. So the operating point is stable, especially against temperature, which is a common problem in all electronic circuits. Not the environmental, of course, it also can change the data because it's temperature. But even if the weather is good, and the environmental temperature is, room temperature is stable, but just because electronics component heat up when there is currents, then the beta will change as well. Okay. So let's take another example. So example 2. So let's add, same example, not same, but similar circuit. We're gonna add, so -10, -5 here, and here is +5. Here is RE equal to 1 kilo ohm. Here is RC equal to 10 kilo ohm. And we connect a resistor to the base. So a little bit harder, but RB equal to 10 kilo ohms. So before anything, locate the direction of the current, the positive directions of the current. So IE is going into the emitter, IB is going out of the base, and IC is also out of the base. Okay, and again, we start by assuming active region. So VEB is equal to 0.7. So this is the emitter. So this is the base. This is the collector. So this is VEB, 0.7. Okay. And we're gonna use the same loop again. So we're gonna use this loop 1. And to make it more clear for you, so we can, draw the actual connection by replacing this 0.5 by a battery, which is 5. And just by looking, yeah, VEB can have, there is a source that can provide the VEB, this junction with a 0.7. So it's either active or saturation. Okay, so from loop 1, you can see that 5 equal to IBRB plus 0.7 plus IE, and IE is actually beta plus 1 IB. This is IE multiplied by R. Okay, so from this you have here in this equation only one unknown. So IB is equal to 5 minus 0.7 over RB plus beta plus 1 RE. So if we calculate this, Mr. IB is 1.1048, and by the milliamperes. Okay. Beta here is 100 again, or what? 30. Yeah, 30. Only 30. Very small. Okay. IC equal to beta IP. So this equal to 3.146 milliamperes. Okay. Now let's check if we are really inactive or not. So we're gonna calculate VC. So VC is equal to -5 and plus IC RC. So this will give you how much? 26.46 volts. And VB is equal to, so VB is the voltage at this point. Okay. It's equal to actually IBRB, or 0 plus IBRB. Because this point is 0. So, and voltage here is in that way. So it's 0 plus IBRB. So it's equal to, IB is known. RB is also known, 10 kilo ohms. So this guy is 1048 volts. So VCB PNP transistor, so VCB, yeah, is equal to VC 2646 minus 1084. This is really big, 25,482. This is absolutely larger than 0.4. So the assumption is incorrect. That means that the junction is forward. And not just forward. This is forward with a massive voltage. Massive forward. It's not 0.7 even. It's a 25 volt. Okay. So the assumption is incorrect. Because active means it should be reverse. So we're going to assume saturation. So assume saturation. So in saturation, still VEB 0.7. What else? Yeah, VEC is 0.2. Okay, and again, IE is equal to IC plus IB. Okay, let's draw the circuit again. And now we have here 0.7. And we have VEC 0.2. Okay, what we have? Yeah, okay. So, first let's get IE. So let's change the color. Okay. IE is equal to, if E is flowing in that direction, so it's equal to 5 minus this point, which is VE, over RE. Okay. How about VE? VE is equal to 0.7 plus VB. So we know that this point has a higher voltage than this point by 0.7. Okay, what I'm gonna do now, I will make all the currents or our variables or our unknowns as a function of VB, the base voltage. Okay, because if we know the base voltage, we're gonna know the collector and the emitter voltages as well, so we can calculate IC and IB and IE. Okay, so we know that VE here is equal to 0.7 plus the voltage at that point, which is VB. So IE is equal to 5 minus 0.7 minus VB over RE, and RE is known, so let's keep it RE. Let's keep it simple. So IE is equal to, RE is how much? How much is RE? It's 1 kilo. That's very okay. So this is 1. Don't convert it to ohms, just keep it in kilos, so IE will be in milliamperes at the end. But do that for all the currents. So IE is equal to 4.3 minus GB. Number 1. Let's do the same for IC as well. Okay. IC equal to VC, the voltage at that point, minus the voltage at that point, minus 5 over RC. Now we want to calculate VC. Okay. Okay. VC is equal to VB plus this voltage. This voltage is VCB. But we don't know this voltage. But we know VEB and we know VEC. So let's do this trick. VEB equal to VE minus VB. Add and subtract VC, so you don't do anything. So VE minus VC plus VC minus VB. I didn't do anything, okay? I just added VC and subtracted VC, okay? So nothing changed here. VE minus VC is VEC, which we know. And VC minus VB is unknown for us. We don't know. And VEB is also known. So this is 0.7, this is 0.2, so we can get VCB. VCB is 0.5 volt. So going back here to this equation, IC equal to VC is VB, which we don't know, plus VCB, and VCB is 0.5. I'm sorry, minus 0.5. Minus or plus VCB. VEC is 0.2. VEB is 0.7. Minus, yes. Okay, so IC is equal to VB. I'm sorry, IC is equal to VC, and VC is equal to VB plus minus 0.5. Plus 5 over RC. Can somebody check for me, please? This calculation, just Chris Koloff, can you please check behind me?
Yeah, 1 second.
Okay. This example is in the book, so I confirm it with the book, but now I have a discrepancy here between the result here and the result here, especially about VCB.
It's fine to me.
They are good? Okay, so I think there is some discrepancy here. This should be plus for some reason. Okay, so VEC is 0.2. And here is VCB. So this guy plus this guy should be equal to this guy. Yeah, VEB minus VB. This is VEC. VC minus VB, which is VCB. And here is VEC to that location. So I don't know, something is not good here. It should be plus, not minus. Basically, we can make a Kirchhoff here. So that means that is actually a Kirchhoff in that, that loop here. Okay. So from that loop, this voltage plus this one equal to this one. Okay, so this one is equal to, this should be plus. Oh, I'm sorry. Yeah. So this should be plus. Yes. So this is VEC, and this is VCB, and here is a plus sign in between. Yes. Okay, now we are good. Sorry about that. So it's a plus, not minus. Okay. and based on that is also plus. So, and the RC is 10 kilo ohms. RC is 10, yes. So this will be 0.1 VB plus, this is 5.5 divided by 10, so it should be 0.55. So IC is equal to 0.1 VB plus 0.55. It is number 2. Okay. Let's continue another slide. So we reached these two equations. So example 2. Continue. So equation 1, that IE equal to 4.3 minus GB. And equation 2, that IC equal to 0.1 VB plus 0.55. Now IB, okay? So let's draw the circuit again. And the actual IB is simple, so it's minus 5, positive 5. This is VB, and the IB is flowing in that way. It is RB. So IB is equal to VB minus 0 over RB. RB is what? RB is 10 kilo ohms. So this is equal to 0.1 VB. Here is number 3. And you know that IE equal to IC plus IB. IE is 4.3 minus VB. IC is 0.1 VB plus 0.55. And the IB is just 0.1 VB. Here you have one equation with one unknown, which is VB. So from that equation, VB is equal to what? Equal to 3.25 volts. Okay. So now we can calculate all the currents because all the currents are a function of VB. So IC, first IB is equal to 0.3125. IC is equal to 0.862, and the IE, just because we did it, 175. Okay, now let's check. So check its saturation region. That means that IC over IB should be less than beta, which is 30. IC over IB here is equal to 2.75. This is absolutely less than 30, which is beta. Okay, one notice again that if you IE doesn't equal to approximately equal to IC, there is a much difference between them. Okay, about maybe more than 4.4 milliamperes. Okay. Okay, let's have a bigger example. Okay. So example 3. So we'll combine now both NBN and NB and PNP transistors in the same circuit. Okay. And again, we wanna solve it and find all the currents. Okay. So before starting, let's first show the direction of the positive currents. Okay. So this is NBN transistor. So this is NBN transistor. And this is PNP transistor. In the same circuit. That's fine. So here is the direction of IB1. Here is the direction of E1. And don't confuse yourself. Here is IC, not this one. This is different. So this is IC1 flowing into the collector. Here is IB2, and look at the difference here. So here is IB in the PNP transistor is going out of the base. Here is IB, which is IB1 of the NPN transistor going into the base. Here is IE2. And here is IC2. Okay. So the circuit looks very complex. We have two transistors, okay, many currents. So one easy step here is to replace that part. Let's choose another current. By H7 equivalent. So we can redraw that in that way to make it more clear for you. So we can replace this voltage divider by H7 equivalent. So replace this voltage divider circuit portion with its Thevenin equivalent. Just like what we did last lecture. So before going into the circuit, okay, we have here, I'm gonna do that again for you guys. So if you missed it last time, here are the 2 points between which this point in here and the ground. This is A, this is B. B is the ground. This is RB1, this is RB2. And here is, I think, 15, right? 15, yes. So first, step 1 in Thevenin equivalent. Step 1, R Thevenin. To find R Thevenin, what we do? We cancel any source. We have here one source, which is the 15 volt. To cancel the 15 volt, we cancel its voltage difference. So we make a short. So now cancel 15 volt source. Make short circuit across its terminals. Step 2, just imagine there is another source here. Just the imaginary source. Okay, between A and B. I mean, A and B is not open circuit. That's why we assume something in here between A and B. So when we look in that direction, what is the equivalent resistance in that direction between A and B? So imagine a source between A and B, and, or let's make it a separate step. So then find equivalent resistance between A and B, which will be in that case. So RB2 is going to be between A and B, and the RB1 also between A and B, because now this is short and this is B, which is the ground. So R Thevenin equal to RB1 parallel to RB2, and this is actually equal to what? Equal to what? Equal to yeah, 100/3 kilo ohms. Okay, step 2. Step 2, finding V7, which is the open circuit voltage between A and B. So we draw again this portion of the circuit. The ground is in here. This is A, this is B. Now it's open circuit here. And we want the voltage between A and B. This is RB2, this is RB1. Here is the 15 volt. Basically, since this is open circuit, so the current flowing in RB1 is the same as the current flowing in RB2. So just a voltage divider. So V Thevenin, which is VAB, the open circuit voltage between A and B, is equal to 15 multiplied by RB2 over RB1 plus RB2, which is 5 volts. Good. We didn't solve the circuit yet. We just, remove a portion of the circuit and substitute by its Thevenin equivalent. So let's have another slide here. Continue. So let's now draw the new circuit. So RE2 RC2 here is NBN RE1 here is a 15 volt, and now we have here R Thevenin and V7. Very big circuit, to make it clear for you, and V Thevenin here. Okay, and we know this is 100/3 and this is 5 volts. Here is RC1 and this is not IC1. IC1 is here. Here is IB1. Here is IE1. Here is IB2. Here is IC2. Okay, so assume Q1 and Q2. This is Q1. This is Q2 active. So VBE1 equal to 0.7. Remember, this is NBN transistor. So we deal with VBE, not VEB. So let's do that loop. V Thevenin equal to IB1 R Thevenin plus 0.7 plus IE RE1, and the IE1 is just beta 1 plus 1 IB. Beta plus 1 IB1 R. And by the way, beta 1 is equal to beta 2 according to the problem. So just call it beta. It is only one unknown in that question, in that equation. So IB1 is equal to how much? Equal to 0.01278 milliamperes. You know IB1, you can determine IC1. IC1 is equal to this, multiply this by 100, so 1278 milliamperes. This is IC1. Okay. Now for the second transistor. So we determined the current of the first transistor. Now we want to determine the currents of the second transistor. Good. Remember that Q2 is also assumed active. So VEB is 0.7. Remember the emitter is here. Not here that like this guy. Not down, it's up. Call this current I. Okay. So at that node, I plus IB2 equal to IC1. IC1 is known, by the way. Here is IC1. So this is an equation in two unknowns, I and IB2. Good. How about this loop? Let's call it loop 2. From loop 2, let's draw the equation for loop 2. We have this voltage I RC1, and we have another voltage here. So this is the current flowing in that way. So the voltage in that way, and we have VBE or VEB. I'm sorry. Yeah, we have I RC1 equal to VEB 0.7 plus IE2 multiplied by RE2. This current is IE2 multiplied by RE2. But IE2 is equal to beta plus 1 IB2. So look at this equation. This equation has two unknowns, IB2 and I. And this equation number 1, again, the same two unknowns, I and IB2. So we can solve them together. So by solving equation 1 and equation 2, we get both I and IB2. So if we did this, IB2 is equal to 0.02748 milliamperes, and I is equal to 12505 milliamperes. And usually IB for either NBN or BNB is much smaller than other currents. Okay, then we can get IC2, just multiply this by 100, so this will be 2748 milliamperes, which is approximately equal to IE2 as well. Now the moment of truth, if we are really active or not, so we must calculate VC1, VB1, VC2, IB2. I will do that very quick. So VC1, check here. We must make two checks, one for Q1, the NBN transistor, and another for BNB transistor. So VC1 is equal to, I will just state down the equation. You guys go and do it. So so the voltage at that point equal to that point, which is 15, minus the voltage drop IRC1. So this will give you 874 volts. VB1 is equal to, here is the voltage at base 1, it's equal to V7 plus IBR Thevenin. So this will equal to 4,534 volts as well. So VBC 1, which should be less than 0.4, is equal to 4.534 minus 8.74. This is actually minus something. Minus how much? I think approximately 4.2. So it's minus. That's fine. So it's so J2 is really reverse biased. So the assumption for Q1 is correct. Still Q2. This is Q1. Now Q2. VC2 is equal to, so where is VC? Here is VC2. This is ground, so it's equal to 0 minus this voltage drop, which is IC2. I'm sorry, the current is flowing upward. So yeah, minus IC2 RC2. Or I'm sorry, the current flowing in that direction. Oh, the voltage, yeah. Okay. You have the same stuff again. So IC2 is flowing upward in, oh, I'm sorry, out, not in. I'm very sorry. Yeah. IC2 should be out of the collector. Yes. Out. So this is IC. I'm very sorry for this, guys. Yeah, these problems usually have, you would make mistakes out of this kind of stuff. So be sure always to locate the correct direction of currents. Yeah. So VC2 is equal to this voltage drop, which is IC2 multiplied by RC2. So this will be equal to 7.42 VB2. Let's see VB2. It's the voltage at that point, which is the 0.7 minus. So it's equal to that point. How did I do that? Oh, VB2, so base 2 here has the same voltage as VC1. So the voltage at that point, because the base of Q2 is connected to the collector of Q1. So don't do that again. So base 2 is equal to VC1. So VC1 is what? Is 874. Now VCB2, which should be less than 0.4, equal to 7.42 minus 874. It's around minus 0.7, something like this. So since it's a minus, so G2 of Q2 is also reverse. So the assumption is also correct for either Q1 or Q2.